I'm very, very happy to continue our colloquium series. This is our second month. We're going to plan to do this every month for the rest of the academic year. And this month, I'm happy to have with us Dr. Fred Martin, who has been at the Media Lab for over 15 years.
No, Media Lab's only that old.
Oh, well.
13 years.
We round off to the nearest 5. He's done some really cool work with a programming language called Logo, which is a lot like a programming language that you've spent a month studying, and doing it from the design side and from the educational point of view. So he's going to talk about his work with us today, and I'd like to please welcome Dr. Fred Martin.
Thank you. So I'll start out by saying a little bit more about my background, but first I want to say I'm really excited to be here and meet you guys. I'm very interested in alternative learning environments. That's been really the theme of my work for the last 15 years. And I think it's really exciting what you guys are doing, and I guess you're the first class, so you're all guinea pigs, and it looks like it's a lot of fun, so I'm a little jealous. I've just left MIT, like as of this fall, for the first time in my life, essentially, since I started there when I was 16 years old as an undergrad. So I'm 36 now, so it's 20 years at MIT. So it's kind of fun to be away, but at the same time I have to figure out what's new, what in terms of what I'm going to be working on. But I do plan to continue work in education and technology, and that's what I'm going to be talking about today. So I guess the main theme of what I'm going to be showing you guys is this sort of. I'm going to start out with some history, going back to as Shai was saying, that the Scheme is the language you guys used. Is that right? Mm-hmm. And I'm going to start out talking about Logo, which is a language that came out of the MIT AI lab, the same place where Scheme came from, and was made as a language for kids. And that's led to a bunch of projects in hardware in collaboration with the Lego company. And the Mindstorms that's on the slide title is this new product. Well, it's 2 years old now. How many of you guys have played with this thing? Only one. You got to get hardware in. Sly and I were talking.
Right,
we got to buy a bunch of. You can just talk to Mike Allen.
Okay. He's right there.
Where is your mic? Yeah. Hi. Yeah, so I'm going to basically talk about, this is a product of the Lego company. It's a computer brick that you can plug motors and sensors into, and then you use software on your PC to compose a program that gets downloaded into this block, and then your model can run away with carrying its own brain. And this is a 2-year-old product of the Lego company, and basically what I'm going to do is describe the whole sort of span of work that led to this. Yeah, so I have my alumni address. That's the best way to reach me. I still have basically my work is on my MIT web pages, so that's the address. And you guys got that by email. This is an overview of a longer talk, so I'm not going to get to everything in what's on the slide here. But I wanted to, this is fun, this part. Brief history of cybernetic thinking. Cybernetics was this term that really came in vogue in the 1940s and 50s as a result of a lot of the work that was done around making weapons for World War II, automatic control systems to guide missiles. But the ideas go way back. And when I was doing some research, some library research for my doctoral dissertation, where I was sort of explaining cybernetics over the years, I found this great history that basically the first upper half of this slide came from this one book by Otto Meyer. And the first recorded history of the idea of cybernetics, a control system, something that measures the state of a system and feeds that back to control the state. So, a thermostat is your classic example in everyday life. Where did that idea first exist? In human history, and it was in China with this water clock. And the way the water, so you want to measure time, and this idea, and these things were actually built. The way you measure time is you have this vat of water, and if you can maintain the water level at a constant level, then it creates a constant pressure on the opening at the basin, and that will create a constant amount of flow, and then you just measure the flow, and there's your clock. Is how do you keep the water level constant? And basically they built the float valve so that you've got this thing that's sitting on top of the water, and when the water level goes down, it lets more water in. So where do you find this in your house? So what was once a water clock is now a toilet.
So we could tell time with our...
Maybe, yeah, you could do a little engineering. And in this history that I found, basically this idea of control systems didn't reemerge in Western culture anyway until, and I mean, I think it was lost in Eastern culture as well, until the mid-1600s when this guy Hubble, who is a scientist and entrepreneur, was trying to basically provide poultry for the French royalty. And he invented the first functional chicken hatcheries using the same idea of measuring the temperature and controlling, keeping it constant by controlling the heat source. And the next big breakthrough was in the 1700s, the steam engine governor. Oh, I don't have a picture of that here. And that was, this is a famous invention that really precipitated the Industrial Revolution. These steam engines were big, monstrosities, and they basically, when the boiler would get stoked up, then the power output would just take off, and the thing basically was like a monster out of control. And so James Watt put together a bunch of ideas. It's interesting if you read the history, because it's a famous name, and at least as it seems from what I've read, he doesn't take credit for having done anything new, even though he's credited with that. He basically said, I put a bunch of ideas together. But of course, that's what good invention really is. So he built this apparatus that you put in the output shaft with these, basically these heavy metal balls that, as the shaft spun faster, they'd get pushed outward, and that with a sort of contraption of levers that would throttle down the steam engine, so you'd have constant power. And that was really critical for the stuff actually being useful. In the 1800s, the way these ideas got transformed is there's this big interest in mechanical automata, basically contraptions and a lot of these were fake. There was things like this mechanical chess player where there'd be some complicated mechanical robot that supposedly played chess, but actually there was a little, basically a midget inside of it who was playing chess. But there were a lot of authentic, very sophisticated contraptions that were just meant to sort of stimulate the imagination, and basically the precursors of AI, building machines that represented intelligence. So there's a contemporary place that the next time anyone is in London, I highly recommend. It's called the Cabaret Mechanical. I actually met the people who run the place. It's a family-run museum. It's small, but they have this wonderful collection of some old and some new contraptions, and they're all really kind of whimsical, and a lot of them are sort of wicked political or satire sort of comments. So it's sort of more there's not sexual stuff, but there's funny. It's more appreciated by adults than by kids, some of them. But anyway, this one I like is because it's the recursion theme. The guy on the left. There's a lot of husband and wife sort of things. I don't know what that one on the right does, but you turn the crank and there's this complicated series of cams that makes this whole little thing play its show. So the Cabaret Theater. So anyway, if you go to London, look it up. Yeah, so I'm just going to go over this part really quickly. But I mentioned the cybernetics, and Norbert Wiener was one of the leaders, one of the people who came up with that term. And a lot of it was driven by World War II and the need to make better weapons and stuff that was more accurate. What happened in the 50s, and this is just a very brief and biased thing, but what's personally inspiring to me is the work of W. Gray Walter, who was a British neuroscientist who basically was also a hacker. And he built these vacuum tube controlled robots. And I'd say, as far as I could tell, he's the first guy to build autonomous robots and treat them like pets. And now this year's most popular Christmas toy is going to be the Poochie robot dog, which was really based on the work of this Sony scientist who built these robotic dogs that were really sophisticated just a couple of years back. But anyway, this guy, Gray Walter, he wrote up these articles that were as if he had discovered a new life form, and he gave them some Latin name for each of his robots and described its behaviors and this. And they're very clever designs in sort of in a lot of ways. I mean, he would get 1 or 2 vacuum tubes to make the thing have 10 different behaviors that overlap in different ways. So it was very clever. But the real special part to me is that he thought of them as being little creatures. And when I see kids building these Lego models, it's so prevalent. It's basically you can't help yourself. And especially when you've built it yourself and it has some, weird kind of interaction with a sensor, or it just does something funny, and you're not exactly sure why, and you just sort of try. It's hard to not attribute some kind of personality to it. Certainly, actually, Mike and I, who have both done work on the MIT 6070 contest, it's very interesting because there's this particular problem that the students are presented with that you have to solve in order to win or to succeed. But the machines that people build are also different, and you can really see a correlation between the personality of the students and the behavior of the robot. And you get these students who are, well, I don't want to. Actually, I'm not even being recorded. I was going to make a fraternity joke, but well, that's enough. Anyway, and then those tend to be the violets, the robots that are a little bit more violent or aggressive, and I mean, it's a lot of it can be stereotypical, but anyway, there's this just real personality that comes out when people build these sort of things. So, Gray Walter's stuff was a direct inspiration to my own mentor, Seymour Papert. And Seymour is a professor at MIT. He started at MIT in the 1960s. He was co-director of the Artificial Intelligence Lab with Marvin Minsky, probably 10 years' time, and is also a founder of the Media Lab in 1985. So Seymour's been doing work for a long time. He studied with Jean Piaget, and that's a famous name if you study cognitive science or child psychology. He's credited as being the first cognitive psychologist, probably before that term was invented, who took what kids said seriously. He didn't think of kids as miniature adults, and when kids had sort of some way of describing something in the world, he actually took literally what they said, that really represented what they thought, and that there were these misconceptions or alternate ways of looking at the world that kids have. He had a theory of phases that you go through. A classic experiment of Piaget's was this idea of conservation, that basically, I think this is still true, if you take a fixed amount of water and pour it into a tall, thin glass versus something more like a narrow, a wide dish that the water will only be kind of flat, kids will think there's more water in the tall glass, up to a certain point where kids realize that no, water is this substance that doesn't change in quantity when you move it from vessel to vessel. So what Piaget found was that basically everyone goes through this period of being pre-conservation where you don't realize that the amount of stuff, you think that the amount of stuff changes when it's moved around, to post-conservation when you realize that, no, it's the same amount of stuff.
Roughly what age does that happen?
Well, that's something that's been argued up and down, and actually I'll respond with an anecdote. I don't know if any of you might know Margaret Minsky, who's Marvin Minsky's daughter. There's a story about her. It's all a very small community, especially when you're still in Cambridge. That, because Seymour and Marvin were doing this work when she was a young girl, and so, somebody was trying to do the conservation experiment with Margaret, and she was like, this is conservation. We did this last week. But a lot of the work post-Piaget has been people, redoing the experiments, seeing that kids much younger than Piaget thought actually have this idea of conservation. And, some people don't necessarily believe that this sort of series of sequential stages is actually true. And so there's been a lot of, he sort of laid the foundation for this whole way of thinking, but a lot of his particular theories have been challenged. So Seymour studied with Piaget in his lab in Geneva, and I guess that would be the 40s and 50s. Seymour also has a doctorate in mathematics. I think he has more than one doctorate. But basically, I think the work with Piaget, and I'm sure he was predisposed to want to work with children, he's dedicated most of his life to creating new materials to enrich children's world, and he's the world of children, and he's really specifically interested in the way technologies changes the way we think. So Seymour is one of the inventors. Let me just finish what's on the slide. Piaget has his theories of learning were called constructivism with a V, and by that he meant that this process of gaining knowledge is something of constructing ideas, and it's very active by the learner. So that's sort of in opposition to conventional ways of schooling, where, I mean, if you look at, the model of learning that would be promulgated by the MCAS, test, it's basically there's a collection of facts, you have to memorize them, we're going to hand them off to you, and, that's sort of, to be pejorative, it's the idea of pouring information into the kid's head. And I think Piaget's idea of constructivism is that it's very active, and you're not even aware of the ways in which children are assimilating and creating their knowledge. But what Seymour adds to this, and he calls constructionism with an N, is the idea of students building real things, and that you're building this computer program or robot or a poem or a song, whatever. But by the act of making something, that thing that you're making reflects back to your understandings, your ways of thinking. It also serves as a social artifact where people around you, your community, people can give you feedback on your ideas. So Seymour is basically saying, let's do education by having people make stuff. It's a pretty simple idea, and I think pretty common sense. So, okay, I'm going to go right to this slide. Yeah. So this slide is sort of an overview of the technology that's been spawned by Seymour directly and then people who work with him. So I mentioned at the beginning the Logo programming language, the work was done at the AI lab. Seymour used to have offices there. And it was really as a result of Seymour seeing the way that the grad students and the other faculty at the AI lab were studying cognition by writing computer programs, by writing scheme code. People writing code as a way of reflecting on how the human mind works. And I don't know why, but basically he said kids should be doing this. And I wrote in my abstract that back at the time, the idea of a kid operating a computer was, just absurd. I mean, okay, so I was less than 5 in the 1960s, but by an image of what computers were like, it was still the punch card era. I guess at the AI lab, things like, shared, I'm forgetting the acronym, but time-sharing operating systems. You could tell me, what were some of the...
I'm older.
Yeah, that's why you should know. Like some of the first, you had one computer and basically you wanted to have a lot of people using it at once, so they wrote the first
Time sharing.
Yeah, time sharing.
Popular in the 70s.
But some of the work was done like the 60s, right? Tops 20 was that? That's a DEC one.
Tops 20 was 1970, I think, or 1971.
I guess, okay, I'm going off on a tangent. Probably the popular image of computers at the time was the big machines locked in a room with punch cards. The practical reality at places like the AI lab and other university research labs would be there'd be interactive consoles where people are actually talking to the machine in real time. So that sort of was the beginnings of that. And that sort of idea of how you interact with the computer, the listener and scheme. You're typing to it, it's doing stuff. It's got a state that you're interacting with. It's running code while you're talking to it. That whole way of thinking about computers started in the 60s at places like the AI lab. And that really inspired Seymour's work on Logo, which is very much like Scheme. It's basically Scheme without the parentheses. And it's instead of being the operator followed by the arguments, it's more functional where you could say the name of the function you want to call followed by its argument. So it's a little bit more like we're used to thinking in that regard. But the killer apps, so they built this logo and they had kids typing at mainframes. They first started doing stuff like computer poetry where you'd have a list of nouns and a list of verbs, and the computer would randomly pick one and sling it together, and the computer would generate nonsense poems. Things like that. List processing, which is a big part of Scheme, was a big part of Logo. The killer app for Logo was the Turtle. Actually, this is going to go to the wrong place. And the Turtle was first basically one of Gray Walter's robots that was controlled by the mainframe, controlled by Logo. So it was, like an inverted trash can that was motorized and had a cable tether back to the mainframe, and kids could type stuff like forward 20, right 90, and then the thing would go forward 20 units, and right 90 was 90 degrees. And so they could drive it around. And then someone got the idea of sticking a pen in it and putting butcher paper on the floor, and then kids could make drawings. So that was like the killer app for Logo. When got the Turtle, that's what really made it take off. And now if you ask people who have heard of Logo, particularly in the school world, what if you say Logo, they say Turtle. So it sort of becomes synonymous, which in a way is a bad thing, because most of what ended up happening when Logo reached schools was the computer science side got lost, and it just became the scripting language for driving the Turtle around. And how many people actually used Logo when they were kids? Wow, still, see, 10 years from now, it's probably not going to be true. So most people know what the Turtle is. What was that?
I just said they probably still will have used Logo as kids in 10 years' time.
Hopefully. You guys will have, yeah. I don't know. All right. What this link is... This... Yeah. So what I was going to... There's a series of slides here. What this is pointing at is back when Logo was... the Turtle was making the transition from being this trash can robot to being the thing on the screen. Seymour and one of his collaborators at the time, Cynthia Solomon, were thinking about, well, the computer Logo isn't just about controlling turtles. It could be about controlling anything. So they wrote this paper, 20 Things to Do with the Computer, and a lot of them were just like basically screen type of applications, although then this was pre-screen, because this was in like 1970. So, it was the computer poetry and list processing and things like that. But like at least half of the things in this paper were imagining Logo hooked up to physical stuff other than the Turtle, and imagining like an environment where kids could build the machinery that's part of the system. So Seymour, he still does this exercise where these are images scanned out of the paper. Try to balance a broomstick versus a toothbrush, and it turns out most people can balance the broomstick, but nobody can balance the toothbrush. And then you get into a discussion, why do you think that? And people who have taken physics will have a very mathematical explanation why that's true, but just sort of about anybody can say something about. First, you could just notice that it's true, and then you could think about why. So Seymour likes to do these exercises where people's different way of thinking becomes an object for discussion. But then you can go further. You don't have to just talk about it. You can actually sort of build a thing and then write a program to try to simulate it. So you could say, all right, let's build this truck, and we've got the hinge with 1 degree of freedom, so it's not the 2 degrees of freedom when it's bouncing on your hand. And then instead of just like sticks of different length, you could have one stick with a mass on it that you can move up and down. And basically convince yourself that this is pretty much the same problem. And that that's not too hard. And then you can build it and actually play with it and say, yeah, it's the same problem. But then you can, basically you stick that thing on a turtle. I guess that's what that is. And then you write a Logo program to try to keep it stable. So you have to put a sensor, a potentiometer in the hinge. So you put a sensor to measure the angle of the rod, and you can make it go forward or backward. And you try. So this is sort of a thought experiment. I don't know if at the particular time when this was written, any of Seymour's students actually tried to build this very thing. But there's a collection of things like this. So really, back in 1970, Seymour's thinking, this Logo's more than just printing stuff on the page. We've got to make it control things. So the screen turtles, most of you have seen Logo. I have to show it. Here's like a contemporary version of Logo. And there's the turtle. The first turtles were like done on like vector screens, so they were triangles, and you could never tell where the point was. What's that? Okay. So I could say forward 50. Oh, and so now it's moving. Oh, I don't know if people can see. Let me make that a little bit bigger.
Pen's down. I think the width is just.
No, pen's not down. So we say pen down. Now let's try forward 50. Yeah. All right, 90. So I can say, whoops. Now the thing was, you'd say, you'd ask kids maybe, can you draw a square? And, they'd keep the forward 50 and right 90. And ultimately, they might realize that you could use this repeat command to draw a square. And what happens when it enters school is we were really trying that Logo would be this, be this environment for exploration and kids coming up with their own ideas and making their own projects. But teachers would just be teaching repeat 4, forward whatever, right 90 makes a square. It would just be that was sort of the ultimate downfall of Logo, is it just got assimilated into the schoolish ways of thinking and became another stupid thing. But you could say, how do you make a circle? There was a lot of work done. Brian Harvey was one of Seymour's collaborators at the time, and he wrote like a 3-volume set, computer science Logo style, where you get into mathematics, and there's another book called Turtle Geometry with Andy DeSessa. You can actually take a serious crack at the sort of set of ideas in Cartesian geometry from Logo point of view, rather than from the Euclidean point of view or the coordinate geometry point of view. So there's a lot of math developed, and anyway, it's a pretty rich world. You could define procedures and stuff like that. Well, Logo could only draw straight lines, so how do you make a circle?
The length of line goes to 0.
Yeah. Yeah, somebody said as the length of the line goes to 0, you approach the true definition of circle. You get something that looks like a circle before you actually hit 0. There was this idea that was talked about at the time, the total turtle trip theorem, which is that once the turtle has rotated 360 degrees, then it's come back, to the rotation where it started, and basically that that will make a circle if you multiply the amount of times it's repeating by the amount it's repeating each time. And you get to 360, then you're gonna close the loop.
You could do that right now.
Yeah. So we'll do repeat 10 times, forward 5, right 36. Oh, well, it's a little bit too small. Let's just make it repeat. Then you have to think, well, if I want the circle to be a certain size, how big does the forward have to be? I'm just going to make it big enough that you can see it. Yeah. Well, that's not exactly a circle, but, you can get repeat 20 times, forward. Well, we're trying to use integers here. Yeah. So that's pretty much a circle. But there was a lot of thinking about geometry, how to get things to line up, and kids would make drawings where they try to make a house, or you'd make procedures, and it's funny to see what happened, because in one of the earlier versions of Logo, before the mouse, okay, so this is mid-'80s, there was a escape key that you could then move the turtle around with the 4 arrow keys. It was the function 9. So there were these big discussions about whether or not function 9 should be allowed, because then kids could not have to think about the angles and distances. They could just put the turtle wherever they want. And a lot of teachers were really, upset that the software had this new function that made their lives a lot more difficult, because then kids wouldn't be forced to drive the turtle around. They could just pick it up and move it where they wanted. So it was a big deal at the time, and now it's even to get the kids to do this at all would be seen as bizarre, because just draw the square with the mouse. So the challenge really is to say, what's the computational power here? What sort of things can you describe mathematically and algorithmically that let you make drawings that really wouldn't be possible if you're just drawing with the mouse? So if you made it, for fractals would be an example that for higher math. But even just repeating a tree in 5 different places, if you define once a procedure to make a tree, then you could tell the turtle, draw a tree here, draw it here, draw it here. So, and this software lets you do animations where you can make the turtle change what it looks like. There's this whole set of shapes that the turtle can be. So we can make the turtle be a bumblebee. And then with logo commands, you can make it be that bumblebee or this one. And then, you can make it flap its wings and fly around. So it's a pretty nice environment for scripting, sort of dynamic things. It's great for making simple video games. So there's a lot of stuff where you can still motivate the sort of programming underneath. And that's a lot of how this is actually still used in schools. All right.
What grade level is this used at?
Mostly the elementary school, upper elementary. Yeah, I mean,
But a lot of the products nowadays are what you say, they're front ends to the real logo, right? They just give you a higher level scripting language on top of logo, and let you like there's something called Logo Writer or something.
Oh, yeah.
Like that.
Well, right, Logo Writer was one of the pretty early ones. This one's called MicroWorlds, made by the same company that did Logo Writer. But that there's logo underneath. I mean, this even has the conventional paint tools. So, if you just wanted to draw the square, you could do it like this. But but there's this whole exploration of geometry and math, and then ultimately, if in the hands of kids who are just motivated or teachers that are creative, you can start to think about types of things that you can create with programming underneath that you couldn't create just by drawing it with the mouse.
What's the little icon of the kid doing this?
That's the undo. It actually has a sound effect attached to it. Yeah, I mean, I think this did come after KidPix. Those of you remember KidPix, it was like a drawing program where the goal, for kids, where the goal of just doing stuff was sort of the activity. It had all these sound effects, and it was really well done. It was really early Mac. It was like a Mac SE days. They still use it. Yeah, it's still fun.
What's it called again?
When I first brought a Mac to my mom, that was like the first thing I had her do. Because you can't do anything wrong. It's just then making a final drawing isn't the goal really. It's just to have fun doing stuff. All right, I'll go back to the presentation notes. We're running out of time to actually get to the Lego side of things. So the sort of software-based logos are on the left side. The thing I was just showing you is MicroWorlds logo. Mitch Resnick, who I work with for a long time at the Media Lab and is faculty there, he, for his PhD thesis, he created a thing called Star Logo, which is a massively parallel version of Logo with hundreds of turtles and for really exploring emergent phenomena. And actually, one of his students right now, one of his PhD students, has been doing a lot of work with teachers at high school level using Star Logo and basically developing a curriculum around studying emergence with high school kids writing these Star Logo programs. So that's pretty cool. That was originally done on the Connection machine. Gee, I guess probably people might not know what that is. Yeah, that was like this computer with 16,000 processors in it. Oh yeah, yeah. For a long time, I think the Media Lab had one of the disk arrays, which has this really elegant, design. It's big, and basically now it serves as a bar. So then it was ported to the Mac, and now it's available in Java. So it's a nice environment. If you go to the Media Lab and search for Star Logo, it's cool software. All right, so then there's this other big branch that happened in the mid-'80s, which is the work of connecting Logo to Lego, to physical stuff. And the real breakthrough is actually the idea of using the Lego materials. Sometime in the probably it was late 70s, Lego created this system that's now known by the brand name Lego Technic, which is, I don't really have many good instances of it here. But it's basically this, here's nothing much to see. This is a little robot, but it's this really nice mechanical building environment with Lego where you have beams and axles. And Mike, do you have any of it here? Not that I'm going to make you leave the talk and go get it. All right, you're going to bring some in. In addition to the puzzles and stuff, we can have like a kit of Lego to play with. Yeah. Right. But it's this great building system, basically. And if there is one core expertise of the Lego company, it's making great plastic and great building materials. Now they're branched off in all these things, and it's a real sort of challenge for them to become brilliant at these other things like they have been at plastic. So some researchers at Seymour's lab, Mitchell Resnick, who I just mentioned with Star Logo, and actually a man named Steve Aka, who just passed away last month, was a big part of this work. And Brian Silverman, who is the chief scientist at LCSI that produced Microworld's logo. Basically, those three people and Seymour created this interface between the Logo language and the Lego product. And it resulted in a collaboration with the Lego company that continues to this day. They're a big sponsor of Mitchell's group at the Media Lab. That led to this series of products. The first product was something that we called Lego Logo, Lego/Logo, because the names are even a match. Lego launched it by the product name Lego TC Logo, and they lowercase the L in logo. So a lot of us were annoyed with that, but everybody just called it Lego Logo anyway. And this is back in the Apple II IBM PC era, and it was this black interface box that plugged into a slot card in the machine, and there was a very simple text-based logo. And then kids could build models and plug. It supported 3 motors and 2 sensors, so kids could build these models and write Logo programs. It was basically just like that slide I was showing you with the guy trying to balance the stick. Kids could actually do this. So that's been around for about 15 years. I joined Seymour's group just when basically the first commercial product of that was done and launched to schools. And what we were looking to do is this is basically Seymour's idea. Let's take the computer, which is the Apple II, and take this interface box, which is about like twice the size of a VHS cassette, and let's make it into something we could hold in our hands, and kids could build into a model. So that was sort of the work that I started doing it was like 1987 when I joined Seymour's group. So we had this series of things, this series of programmable bricks. This is actually a picture of a more recent one. This is one that was done in 1994. And I did a bunch of work with kids and teachers. We created this prototype, made like 100 of these, brought them into schools. So I'd like to actually show a video of some of the classroom work that I did. And so let's see if I can. Oh. Hey, it's working. Oops. No. This is footage from a 4th grade classroom. We did a workshop with a group of teachers, and so the teachers had this experience of building these Lego models and writing Logo to control their model. And then we started to think, well, what are we going to do in the classrooms? What kind of activity should the teachers do with their kids? It's not just going to be about building Lego. It has to be something that has a larger context. So the teachers came up with this idea of building robotic animals. And partly that was, we wanted to make sure that it was an activity that would be inviting to girls as well as boys. 'cause the activity I'd done with the teachers was a robot design contest, sort of modeled after the 6270 contest at MIT. And they had a great time, but they thought, for our kids, we don't want it to be competition, and we want something that girls and boys will both like equally well. So this has turned out to be a great theme. This is the first...
Plan for the turtle.
I'll do a little interview here. So.
See, you touch sensor on its head. Uh-huh. Uh-huh, so the head moves. Mm-hmm.
And the light sensor, he'll be going away from the light.
Oh, so because he's scared of the light?
Yeah, but I'm not scared of the light.
Mm-hmm.
This is the first time they got it like turning and the touch sensor working. I work with two different teachers in this school, and this teacher, John Bellotta, actually, shortly after I was doing this stuff with him in his classroom, he ended up moving out of the classroom and taking sort of a technology district coordinator role in his school system, because he really believes in this sort of activity and wanted to help other teachers get it going in their classrooms. Now this group of teachers that I work with, it's still going. This is 6 years old, this tape, and there's like an annual like robot show. I guess it's called Robotic Park. And so there's a lot of teachers, and it's in the state of Rhode Island. It's like a 2-hour drive from here. But it's really nice to see things take root in a classroom. And what I've found in working with schools for like 10, 15 years now is bottom up works much better than top down for really making things change. That when you get teachers who are really motivated, they want to try something new, and then teachers teaching each other is the best way to actually get new ideas into classrooms. Like, I can go and say, hey, this is a really great activity. Let's do a week-long workshop and lead a really good activity for teachers. But in order to say, how is this going to work in a regular classroom where the kids are there every day, classroom management issues, all that stuff is teachers working with each other is just the best way, in my experience. So this stuff has really taken root in this group of schools in Rhode Island.
Does this work the same way Mindstorm does? You hook it up to the computer and program it to the computer?
Yeah. This is the last little snippet. It's really exactly the same at a conceptual level, and I think this work is what led Lego as a sort of company to come to the decision that this programmable brick stuff really is for real. This is actually an interesting collaboration. This group of 3 girls was the project team, but when they wanted to build that dinosaur head, there was this boy in the classroom who was known in the classroom as this great artist. So they basically had the boy do the body for their robot. So it sort of breaks some of the gender stereotypes.
Outsourcing projects.
And plus, they had the only sort of you would call violent project. Because that, sorry, there's no stop button. I guess I'll hit play again. No, that doesn't do it.
That's not button on that big Commodore either.
All right, well, just forget it. That dinosaur was only half of their project. This was done just when the first Jurassic Park was out, and that was like the theme, the robotic park of animals and stuff. So the other part of the project was the Jeep carrying a flashlight, and the dinosaur hunt down that Jeep and knocked it over. Yeah, so this, I designed this prototype, and we used it in like 6 classrooms at the time, and this really did lay the groundwork for Lego to say, wow, this stuff really works. 'Cause previous prototypes had been really flaky, and basically if me or one of the other people in the group left the classroom, it would immediately stop working. And, it just wasn't robust, so teachers couldn't use it on their own. And like the hardware that we gave to the school was like, it was only like last year where they returned it to me because the Lego product was out. Yeah, so here's like a publicity shot of the Lego programmable brick, which you can see is very related to the red MIT programmable brick. They came up with an acronym that basically there's no other things in the world called RCXs. It doesn't actually stand for anything, but it's unique.
How much do these things cost these days?
The way that it's marketed is it's marketed as part of this thing called the Robotics Invention System. And it's this, you can buy in the toy store. This was a breakthrough because a lot of the work inside the Lego company was done in the education division, because previously their stuff had only been, the computerized stuff had only been sold to schools. And basically there was a new vice president inside of Lego who saw this thing, and this guy also is very energetic, and he also came from outside the company, whereas often they would promote from within. So he was a free thinker, and he saw this stuff and said, this isn't just for schools, this is like the next big toy. And for the last 2 Christmases, it was a big toy. So you get this package with that brick. You get the software. There's an infrared communications device that plugs in the serial line. You get 2 motors. You get 2 touch sensors. You get a light sensor, and then 700 additional Lego pieces for building all sorts of stuff. And it's $200.
What's the memory in this brick? What size?
It's got 28K of static RAM. It's got basically an 8-bit processor with some 16-bit math instructions. It's sort of low tech in a way, but it's it's perfect for what it's intended to do, which is to build these little control programs for Lego models.
Well, you could easily write a program that has a hit a wall, back up, look for.
Okay.
Oh, I see. There's enough room to have it write programs to have it do reasonable things on a living room floor.
Oh yeah. Well, there's this huge like hobbyist community that sprung up like immediately around this thing. People reversed it. I mean, it was incredibly fast. How it was incredible how fast this thing was fully reverse engineered, published on the web, and it really took Lego by surprise. They thought they'd have at least 6 months, and it was almost like the day it was out. And I think there was some information leaked, not by me. I was very careful, but some people did leak information. And I know who they are. They weren't MIT. Yeah.
So how much does it weigh? And also, do you put batteries that will run your Lego creations? Does it run off of
Yeah.
Why don't you repeat the question?
Okay, the question was how much does it weigh, and do you put the batteries that run it inside the device? I'll pass this one around. It's pretty light when there's no batteries in it, but it takes 6 AA cells because motors draw a lot of power, and basically you need a lot of battery to run the motors. So then it becomes heavy, and it actually is a bit of an issue for a fledgling Lego designer to build something that carries this and doesn't fall apart is not trivial. I should have the batteries in it to give you the full sense of what it weighs, but it's nice and light when there's no batteries in there. Yeah, so it is fully autonomous. The things run around on their own, sort of just like the video showed that the MIT prototype, and that one also had the batteries built in.
Are there light sensors on it?
You can plug a light sensor in. All right, I'm just going to kind of finish off with where the work was going at the Media Lab since that came out, the RCX brick. And what we started to work on after the RCX was sort of launched was something that we now call the Cricket. And this is like, there's a question about how much RAM does that have and how fast is it and this. The Cricket is like 1/10 of all those specs. It's run on this chip called a PIC processor, which is basically the processor that goes inside of a mouse. So it's like pretty simple. The the cricket can only do a couple motors and a couple sensors. But we built the sort of a software environment that's in the same spirit as Logo, so that you can talk to your cricket from the keyboard as if you're talking to the Logo turtle. So let's see. Let's see if I have another slide that shows anything nice. Oh, yeah. This is a project built with the cricket. This is actually done at Wellesley College. There's a couple of faculty there that we've been working with. One of them is a CS professor who's an MIT grad, Franklin Turbach, and then Robbie Berg, who's a physics professor. And Robbie really, he came and did a sabbatical at MIT and saw the robot design contest at MIT and said, wow, this is really great. I want to do this kind of stuff with my students. But sort of similar to the elementary school teachers, he didn't want to do a contest. So he came up with this idea of doing an art studio, where basically it's very open-ended. Students have 1 month to build these models and program, get to do something. You can build anything you like, but you're going to show it off at a gallery opening at the end of the month. And there's wine and cheese served. So there's a whole great range of things, and a lot of them are really interactive. Like you don't just sort of watch it, but you do something with it, and it does something back. Sort of a lot like the Cabaret Mechanical things, where you turn the crank and something happens. So this is one of those projects using the cricket. You can see right there is the cricket, so it doesn't weigh very much. And the woman who designed this was really into crew, so you see the connection. That might be the only picture I have of a cricket project. Whoops, went all the way back to there.
What does that do?
I think it just rows around. Oh no. Lost track. Oh, it has a sound sensor. The pipe cleaners are holding up a sound sensor. So I guess when you clap, that's the motor right there. And you can see the gears that run the paddles. It looks like, yeah, this little red thing is a motor too, so it looks like it has some steering capability. But I don't know how that, what the control program was, why it would steer one way or another. There looks to be a sensor there. I think maybe if it hit something, it would try to back up. Yeah, that's definitely a touch sensor. I have a feeling it didn't do all that when it was actually being showed off. I think it paddled around, and that was enough. Yeah. So I wanted to actually in the abstract, I wanted to actually go into a little bit of the technology of the cricket itself, but we're sort of yeah. All right, let me show you okay. I'm going to show you one of the first demos we built with the cricket. And partly, why do we call it cricket? One of my colleagues, Rick Borovoy, came up with the name. So we had this idea of, it's not like you just have one cricket. If we were to give these to people, we give you 3 crickets at least. Because they have communication built into them. So every cricket can talk to other crickets. So we had this idea of the insects sort of chirping in the fields and listening to each other and stuff. I don't know where I could put this where people can see it. Well, we'll see if it works on the... Can people see the floor right in front of me? All right. This is just a little quickie demo. We have these 2 tiny robots that all they are is a cricket with 2 motors. But they can see each other, and they're a dance team. So when they see each other, they get all excited, and then they go and do a dance.
You guys want to bring that table? Maybe we can put it on the table.
That is
One, two, cha-cha-cha.
It is. It's a cha-cha. It's the cha-cha. That's excellent.
Let's show everybody.
Rick and I actually spent a lot of time, on the particulars of the dance. It was kind of sad.
One, two, cha-cha-cha. Everybody.
Can they tango?
what's the green and the red? Sending and receiving?
That's the motor. It's a motor indicator. There is you probably can't see it. There's a yellow LED that's wired in series with the IR transmit, so you can easily you can see what's
It is
transmitting.
IR though.
Yeah, yeah. So we put something opaque between them, and hey, I can't believe you actually see through that. I think there's only 2 or 3 states in the program, so they'll keep going until they. It's reflecting or something.
Just
I might.
gotta dance.
All right. All right, we can come play with them afterward.
They're programmable as well through the same plug-in and serial port kind of thing?
Right. So let me actually show you. Unfortunately, I didn't bring any peripherals, but I can do math on the Cricket. So here's a Cricket. Here's the serial. We have our own serial to IR hardware. Here, I'll just put these up here. Oops. Okay. Okay. So we actually built the environment. The software environment for the Crickets is built inside of this logo. So this is sort of proof to computer scientists how powerful Logo is. We actually built a Logo compiler inside of Logo. So that's very much in keeping with the scheme and Logo spirit. So if I type beep, what's going to happen is it's going to compile beep, and then it's going to transmit that to the Cricket, and then it's going to tell the Cricket to run what it just sent it, and the Cricket will beep. I don't know if you already hear it. Uh-oh. Oh, I didn't hit return. Here we go. You'll hear it? Yeah. So I could say repeat 3 times, beep, and I'll have to put a wait 1/10 of a second so that they're separate beeps. Right? So we can say, there's nothing plugged in, so I can't really do very much. There, so 6 times. Yeah. And you can define procedures. It's not just. Sorry, what was that comment?
Try pi times.
We could do some numerical, like integer approximation for pi. You can do. Did you guys do Fibonacci example? You can. All right, let's see. If n equals 1, return 1. And the stack is really short, so the second one is also 1, right? Oh, it's not return. God, I've been programming too much in C. Yeah, God, that's embarrassing.
It's embarrassing if your neurons were filled with all that information.
It just shows you what I've been programming in last fib of that. I don't think we need parens really. Well, we might.
Arithmetics are infix
Yes.
by default. So actually, if you don't have parentheses, it doesn't do the right thing.
Well, we have this we try to make the compiler as simple as possible, so there's no precedence. So what I know the last one would work, because basically we would go through and say fib needs 1 input, and then that would work.
Right.
So I think it would.
I think this is going to work.
Well, this will definitely work. Yeah.
If you left the parentheses out, I think it would say negative.
Oh yeah, it would
plus
just bind those two together.
Right. It would bind
Yeah.
those two together, and then it would try to right.
Yeah. All right. So let's download that program.
Or it might. Maybe
So it took up 44 bytes to do that. And now we can say repeat fib 4. What is the next one? 3. Is that 5? Is that the answer?
1, 1, 2, 3, 5.
1, 1.
2, 3, 5.
So that'll be 3. Yep, it worked. Well, most kids wouldn't write that program. And actually, because the first Cricket we made only had 256 bytes of code space, right? So this took up 44. So that would be, like 1/8 of the, less than that, 1/6 of the code space. But it wasn't actually a problem for kids because, they're just writing a little bit of control, and that demo is actually built using the first round of Cricket. So we just barely fit to get that whole thing going in 256 bytes.
I'm unhappy that 5 is the same number as the beeps.
Okay, so it should be 8 then, right?
Right.
Oh. I know what's happening. Yeah. There's when the stack overflows, it beeps 5 times.
We can write a tail recursive.
Yeah. Okay. No, you can't do fib tail
We can do
recursive.
tail recursive. You have to just throw in 4 parameters or something.
It does do tail recursion, yeah. So.
So who can do that in their head?
Is the dance program written in this?
Yeah.
So you can do motion and you can
Oh yeah. So there's
control the input from the sensor.
there's commands here. I guess what we'll do with this
Is
is
that like an event model or something?
it has
How
a,
to deal with the input from the sensor?
okay. Here. I'm not going to reprogram these because I've lost the development environment that works in the first version. And also has a different IR, so it would be a real pain.
Why would fib6 overload the system?
Now that's a question you should be able to tell me. The stack depth is only about like 4 levels deep.
So this is horribly exponential, right? These are
Yeah.
terrible. Right? You all know this is terrible. Yeah. Humor me.
Yeah, I could probably only do fib of, well, let's see, could you even do fib of 3? So fib of 3 is 2. So, but at least it's recursing a little there, rather than just giving you the answer. So let's see if we could do fib of 3.
Recurse too much.
No, I can't even do that. Wow. Wait, is this working at all?
Are you going to try 1?
Yeah. Well, that couldn't go wrong.
It's just
Wow.
a bad way to do it.
Yeah, it's just the stack is really short. And because the repeat expression also is using up stack to get, because the argument for the repeat has to get pushed on the stack. We're limited by the RAM that's in the PIC chip. It's the biggest resource limitation in this system. Because the core execution loop is something like 300 logo instructions per second, which, that's not super fast, but, how fast do the robots move, right? Not very. Yeah, let me just show you how to, so I plugged the 2 motors for that little model into the Cricket, and so now to get the motors to move, there's just commands for the motor. So I can say motor A, turn on for 1/10 of a second. Yeah. It's going to go straight just because, well, let's see. If motor B is wired backward, it might.
So you turn them on rather than specify a distance?
Right. It's timing based because it doesn't know how far it's gone.
Right.
Yeah, and that's actually one of the first things that kids deal with is they think that like particularly if they've had the Logo Turtle background, but even if not, they think I want it to go this far, and then they've built the model, so who knows what the gear ratio is, what size the wheels are. So the first things they have to discover is that you control it with time, and then you can make a correlation between time and distance. And then the next thing you discover is that one day, 5 seconds will be the right amount of time, and the next day it's not. So the model doesn't do what you wanted it to because the battery level changes, or the wheels slip differently, or it's not exactly positioned right. So there's a lot of sort of learning about real-world systems that kids do when they go through these projects.
Has anyone ever done a kind of placebo test, if you like, with kids who've been through this kind of environment, as opposed to kids with very similar situations who haven't, and what they go on to do, and what their aptitudes are and so on?
Yeah, those long-term studies. I don't. I mean, there's nothing systematic that I'm aware of having to do with logo. And it's a valid criticism of our work in general that we make these arguments about why this is valuable for kids and schools should have activities like this. And then someone will says, yeah, well, you've been doing this for a while. Where's that study? And we don't have it.
Right.
And I think partly it's because that sort of study can't realistically be done, because there's just so many factors in over the long term of a kid's growing up in their life and school, and I just don't think it's not a reasonable way to look at what the effects of something are. And I mean, I think the way I would get criticized back by saying the tests that do try to say what the effects of a limited intervention are also those are flawed results in and of themselves, even when you're claiming certain results. And I think the MCAS, and it's part of a national movement towards increased testing, and I think it's a disaster in terms for learning. Massachusetts Comprehensive Assessment System. So we have more anecdotal stories. I mean, there's definitely kids that I work with personally who I know it made a big impact on their lives. And I worked with a group of kids at a vocational school, and vocational schools are for kids who aren't doing well at school. And one kid in particular I worked with, it was 2 years that I was meeting with him once a week as part of this class that I was doing. And the second year, there's a big transformation in his whole attitude towards himself and school in general. And he did some great work. And so you can see those sort of things. And most of the teachers that I work with will have examples of particular kids in their class who aren't doing that well at school. The conventional school activities don't appeal to them, and they just have a blossoming when this activity is brought into the environment.
What was the age of the kid you worked with?
That kid was like 14, 15. It was high school, yeah. But most of the work I do now, and I think where this stuff is most successful, is at the elementary school level, like anywhere from first grade through fifth grade. And it's not so much based on the age of the kids as it is more on the nature of the educational environment. That in primary school, you've got one teacher and one class of kids, and time is much more fluid. You can set up activities longer than 45 minutes. And then the Lego building activities become situated in the larger context of learning. It's not just about making a robot. I'm doing this project in Ireland with the commercial Mindstorms. And there we're doing storytelling and narrative, where kids are building models that explore some history. It could be local history or world history. And they're making sort of animated dioramas that tell a story. So, and that really, that sort of way of working, you just can't do it in high school now. The curriculum's chopped up, and the science teacher doesn't talk to the history teacher, and there you are. Let me just mention how you do sensors in this environment. One way you could do it. Here, we'll get rid of the fib program. I don't have a sensor. Oh, I know what I could do.
Here's my fib tail recursion.
It's just the second one of these, or do you need them both?
The second one is just neater than the first. They're both probably wrong. You just have 3 parameters, and the first one counts down to 0, and then when it gets to 0, it outputs the first parameter.
Uh-huh.
I think that'll work. Fine.
All right.
That's a class where you have it.
Okay. I'll have to leave you a cricket then. Equals 0.
0, I think.
Okay.
So the colon defines a variable?
Yes.
The colon says look inside the value of the variable. The colon is short for a function called thing, which takes the name of the variable, thing, quote, and says the value of what's inside. What's the equivalent for that? There is no equivalent for that. In Scheme, everything's evaluated. Here you have to say evaluate this specifically as a variable name.
Is that the logo thing, or that's the...
It's a logo thing.
It's yeah, it's logo. Okay, so if n is 0, you're going to give the result, which is in the first.
Right, so you need to call this like fib511. You have to initialize the first and second to 1, 1.
Okay.
And then they start, so 511 will be the same as 4, 1, 2, which would be the same as 3, 2, 3.
Right, so you count down, you give the answer, and the second parameter. Yeah, might as well.
Yeah,
Oh, no, that should work.
Get away with it because it looks at the arithmetic operators and does an infix. Looks left and right rather than. It's a little. It's more user friendly where the user is a kid than the scheme.
Yeah.
So I think if you didn't do it, it might work. Then.
Hey, it's shorter, 31 bytes. Okay. Well. All right, we'll do fib of 1.
Yeah, you have to do fib of 1.
Oh.
Fib of 5.
Hey, look, it trapped the error. Okay, so we want to do 1, 1, 1 would work then, right?
That should just be.
Well, let's go all the way up to 5. That's our non-test.
Go for the gusto.
Well, that was, yeah, but we don't really know.
Try 6.
So 6 should be 8. Oh, it still blew the stack.
What is the stack you said?
I think it's like 4 calls, though.
This is Talry.
Oh, you know what it is? The arguments also pile up. So I think we don't even get much of anything. Let's try like 2. Hey, that worked.
Let's try.
3. 3 should be 3. Oh, all right.
I'm cooking.
And then 4 should be 5.
Right.
Oh, but
that may
we don't know.
But it
Yeah.
seems like the beats are quicker. When
Oh, yeah?
you overrun the stack.
Oh, that could be. Oh, here. Right. Here we go.
So put an 18. Let's see how quick it is.
Right. So 3 is 3. 4 is 5. Yeah.
Hey, good one. Good ear.
That's nice.
Wow, so this crashes.
Okay.
So I wonder if the interpreter knows this is tail recursive. Because if it's tail recursive, it shouldn't be generating a stack, right? It's just
Oh, it's just calling
it's just
itself.
calling itself, right? You're not doing anything.
You're right. Yeah, it should just be a go-to.
And it's not part of the if. It's not like it thinks it's in the else.
Right.
Notice this is tail recursive.
Why don't we do factorial instead?
Oh, wait, no, we don't. Oh. No, because we're outputting. We have to not do an output.
So,
You actually shouldn't even need the
oh,
output.
yeah, get rid of
That's
the
it.
output. Yeah.
That's it.
Get rid of the output. Then it'll work just fine. No one will go up to 100.
Let's try 6.
Oh, fib. It
This will be fine. This will be okay.
No, it's because fib outputs something.
Yeah, but the output now is down in the base case. So as long as it sees that the recursive call is the last thing in the program, it should know it's tail recursive.
The language doesn't let you make a procedure which sometimes outputs and you see basically if fib is going to generate an output in that call, and so you have to do something with it. We could throw it away. But then how?
You have to do something? Oh, because it's going to say it has an output. I don't know what to do with the output.
Right.
Well, I think in tail recursion, try this because I
Yeah,
don't
no,
know about this, right? I think tail
it already
recursion
did
will-
that.
What is that?
You don't say what to do with fib and fib.
Oh, it doesn't like it.
Yeah.
You can say ignore, but then it's not going to know it's tail recursive. So what's the point of that?
Yeah, I guess it doesn't. I guess it doesn't do the. I mean, I know it'll do tail recursion if you're just counting down and you're not returning
Right.
anything.
Yeah.
We could have it stored in a global, and then
All right. Well,
We could have a third
you were in the
variable.
middle of
and
something before I
apply the
tossed
fib
it.
to the third variable just to throw it away.
then how are we going to get it back out in the final time?
Well, we want to output the first 6.
Well, we could have.
I don't think there's a good solution. Because it's not really doing it's not doing all cases of tail recursion.
If you type output, it should also know it's tail recursive, but it doesn't. Huh?
Right. I think that's all it is. That the right answer is for to output it, but
Yeah, it's not getting it. Okay.
oh well.
Anyway.
Well, I was going to show sensors. But I'll just describe it because I don't actually have a sensor to plug in. I mean, I could simulate a sensor by sending an IR pulse. But basically, you build an infinite loop, and then you just test the sensor value. You say, if the sensor is this, do that. If the sensor is something else, do the other thing. And then we also have, so that's sort of a polling-based model. We also have an event-driven model where you can say, like, when you can set up a daemon, basically. You can say, when this condition becomes true, take this action. And that's sort of a nice way to think about sensors. That, like, typically you're building, particularly in the creature case, you want it to respond when the touch sensor's hit. So you don't want to have to think about, oh, I'm making a loop and I'm always testing to see if that touch sensor's hit. So the software gives you the capability to say, you know, when the touch sensor's hit, take this action. Because of the resource limitations on the Cricket, we can only have one of those daemons, which is limiting. For the software like this that we've done for the RCX brick and our earlier red brick, we could have 8 daemons. And that approach of thinking about the sensors as being sort of always active and triggering when conditions are met, we built that, we sort of made a design that LEGO implemented in the commercial software that ships with their brick. So there's, it's an iconic sort of environment where you're dragging blocks and snapping them together and there's text inside of each block. So it's vaguely logo-like in that there's sort of there's commands and you know and arguments. It's not really logo underneath. You couldn't do this program in the environment LEGO built. But it's very easy to use. It's great for kids who have never programmed before. It like frustrates the bejesus out of anybody who has programmed before because they want to do something like this. But it's easy to use, and you know it gets. And the daemon model is really the right thing, I think, for most of what kids want to do. You want to be able to say, when this touch sensor's hit, do this set of stuff. When that other touch sensor's hit, do this. When the light sensor changes, do this other thing.
Their lives are event-driven.
Yeah. So I'll just close by pointing out this work that we did on the crickets. We just wrote a paper that I can't see the scroll bar. It's off the screen. Okay. Here. That was printed in the IBM System Journal. They did a double issue. That's all Media Lab work. So we got a paper into that. We came up with this terrible name, MetaCricket. But a lot of what people have been doing with crickets within the Media Lab is there's been a lot of people, other researchers at the lab, who've been using them to prototype their own systems, their own sort of computational physical systems. Because you saw how easy it was, right? We wrote Taylor cursor programs that didn't work and turned motors on and off in no time at all. And there aren't many things like that out there. So there's I'm just going to scroll through this and show some of the projects that people have done. So I explain about the virtual machine inside the Cricket and how the software works. Here's where I wanted to come to. One of the big innovations that sort of happened by accident. Oh, come on, what's it doing? Oh, now the network isn't working. No, but we got to here.
Yeah, but this is how our network works, or lack thereof. It'll eventually probably find it.
Okay. Well, what we built. There we go. Oh, it's lots bigger. What that shows is in the sort of center, a little bit to the left, is a Cricket, and then there's a bunch of stuff plugged into it. So at the beginning I said the Cricket only has 2 motors and 2 sensors, which is sort of true. It has built-in drivers for 2 and 2. But it has a peripheral interconnect system that lets the one Cricket talk to like a dozen or so other things. And we came up with this idea of basically packaging the intelligence, sort of the software drivers that go with the other thing itself. So like this is a 3-digit LED display. And on the back of that board is another one of the PIC chips, the same processor that runs the Cricket that's got drivers so that knows how to run the LED display. So then the Cricket just has to send a tiny message saying, hey, throw this number up, and it works. We also run power over the line, so it's really just one wire plugged in. You could have all these accessories. So this is a sound sensor. This one here is a MIDI synthesizer. It's shaped like a boat. And that one was sort of a breakthrough in our work because we didn't design it. And the people who did design it was another group at the lab, and they built it for a particular purpose. But they happened to put a PIC chip on the thing, and they were just controlling it over a serial line. And when their project was done, they had a bunch of these boards left over, so we're like, hey, we can plug that into our Cricket. And we just programmed the PIC chip on that board to talk our protocol, and suddenly there was a MIDI synthesizer that was part of the Cricket system. And that one really led to this whole, there were a bunch of music projects that people ended up building with Crickets. I think I've got...
How long has the Cricket been around?
The first ones were like 4 years ago, but I think they've really taken off in the last 2 years. This one is a Play-Doh music synthesizer. So it's like dead simple. Play-Doh has, it turns out, is like got a lot of salt in it. So it's a great conductor. So basically, I mean, in the electrical sense, but in the musical sense as well. So we just have these two copper electrodes. They plug into the resistive port in the sensor, the resistive sensor port that's already there in the Cricket, and then you just write a one-liner that translates the resistive reading into some music command. You could do whatever you want.
You sort of squish the Play-Doh around.
Yeah, and it changes the resistance and makes all these fun sounds. So that one was just like kind of a simple demo, but then some other people in the lab built some like more serious music toys. People in Todd Mackover's group, who's one of the professors that does computer music at the lab. He's the professor. That's his area. So one of his students named Gilly Weinberg built this thing. He calls it the Squeeze Man, and that he took like miniature koosh balls and embedded some kind of pressure sensor into them, and then those just run to the Cricket sensor input, and basically it's just here's sort of the block diagram. There's two of those squeeze sensors running straight into the Cricket, and then that MIDI boat music synthesizer. But he's like both a serious mathematician and a computer scientist, serious musician, sorry, and a computer scientist. So he had a very complicated mapping, more so than the one-liner I was just describing with the Play-Doh, that I didn't really understand. But so he was exploring some kind of far-out ideas in mapping, and he was able to prototype the thing with basically this off-the-shelf, within the context of the Media Lab hardware, which for him was very liberating because he's not a hardware guy. So he was able to build this demo, to explore the music ideas in really quick fashion. He ended up doing another project with our stuff that, God, this stupid browser loses state when you go back.
Would you see this as a sort of parallel to the sort of basic stamp?
Yep, I'm glad you mentioned that, because that's the closest thing that exists in the commercial world is the basic stamp. The basic stamp is a little board that includes the PIC with a virtual machine, so a lot like the Cricket, and it has a compiler that sits on your Windows box that uses the basic programming language and compiles into bytecodes that then you can stick on this little board. So at the top level, it's really very much the same as the Cricket. The big differences is that we include some stuff on the Cricket itself that they don't, like the motor drivers, the sensor drivers, and the IR communications. So you sort of get a lot right out of the box with the Cricket, whereas with the basic stamp, you have to build those circuits, which is fine if you're an EE person, but if you're not, that's going to be a barrier. I'd say that's the biggest difference. We have a different idea of how you connect other peripherals, and we have like a nice collection like this MIDI synthesizer and a bunch of things, whereas the basic stamp, there are some of those things, so I shouldn't say that's a profound difference. We also have the command line, where they don't have the command line, so it has a much more interactive scheme or logo-like flavor than theirs is just compile, download, and see what happened. But they're not they're not that different. So I'd say until one of the things I'm hoping to do now I left the Media Lab is get crickets out into the world. So we're trying to get MIT to release the technology, and basically it basically boils down to a conversation with the Lego company and making sure that they don't feel threatened if the cricket got into the world. Because I don't think it shouldn't be a hard decision for them to make, because it's not the same market. People who want the RCX brick aren't going to buy crickets. And
So the cricket is not currently sold publicly?
Correct.
Okay.
And we haven't even released the full specs of the design. You couldn't go to the website and download enough information to build one. Could not. But we're hoping to solve that over the next couple of months. I actually have a meeting later today to work on that. And the worst case is I'll be able to license the stuff directly from MIT, regardless of what Lego thinks. But I don't want to, it's more important that I don't get into an adversarial relationship with Lego than.
Lego's powerful.
Well, they are actually. No, but I know a lot of people inside the company, and I've done consulting work for them, and so.
Just don't call them crickets, call them CRKTs.
That would really get to them. RCX is. Just rearrange the letters. It's almost the same ones in cricket. I never noticed that. That's almost true. Maybe we should stop here.
Yeah. Do we have questions? Sarah.
Do you think these will always be on such a small scale, or do you hope to build them to something perhaps more durable?
Actually, I was telling Shai at the beginning, we were just talking to each other, I'm joining a startup for the next few months that's building something very cricket-like, except that it's IP-enabled. So we're making something that's sort of at the scale of the cricket that you can plug into a TCP network and talk to it using standard internet protocols. So this is a startup, so we're hoping that product will sell in the millions. Units, right? Hopefully dollars as well.
And the secret, but I am actually a prototype of that. Fred to send me the right control.
Now it's all clear.
Turn me off.
I'm not sure if that's sort of the direction of what you're asking, though.
More I was asking, because I know, was it Pentium that just recently came out with a chip that's maybe 3 inches by 3 inches. It's got all the power of a regular computer. It takes 5 volts to power it, but it's got up to 64 megs. It's something that's, I didn't really look at your brick, but it looked like it wouldn't be much bigger than that. And you'd have a lot more memory. You'd be able to be much more, I don't know, powerful, but...
Yeah. Well, a lot of people, when computer science people, when they actually read the specs of the cricket, and I was saying this, that the core instruction loop is like 300 instructions per second, which is ridiculously slow. A Pentium is 300 million or something, right? Yeah, it is 300 megahertz. So they're not at the same scale at all in terms of computational power. So a lot of it is, I was saying that James Watt didn't feel himself as an inventor because he was just putting ideas together. A lot of that you could say is true of the cricket. There's not anything fundamentally new there. It's just a novel combination of stuff that's been around that sort of lets you do things that a novice can do, things that beforehand would require a lot of specialized expertise. And that was the driving philosophy of Logo 30 years ago, and I think is still true of these technologies. And if you look at the Lego yellow brick, which got passed around, there's a whole bunch of people that got turned on to robotics that never tried it before. The first year, like 2/3 of their market was like people like ourselves in this room, adults who wanted to play with robots and never could until now. So I think that's the enabling power of technology, to sort of let people have access to ideas that previously seemed too complicated, too esoteric, and it really isn't that way. It's just packaging it so you can get your hands on it. So I know that doesn't answer your question, but...
Well, part of the idea is that it's stripped down because the purposes you use it for don't need
Yeah. Right, you don't need a Pentium.
Right, we're not forecasting the weather with these things.
Right.
We're letting them find outlets on a wall or something.
Right.
Yeah, John?
I didn't catch exactly what the musical Play-Doh did. Did it kind of like reshape and dance to a musical input?
You squeeze the Play-Doh, and depending on the code that reads so the Play-Doh just returns one parameter. It's a resistance reading. And so that can get mapped into different ways. My favorite demo is one that maps it into the percussion track on a MIDI synthesizer. So basically, actually the program that I put into it when I would show it off is every 1/10 of a second it reads the Play-Doh value and generates a percussion noise.
Right, so it's an instrument.
Yeah, right.
I was thinking of it more as, it'd be great if you could put some musical inputs in and see how it reacts to Beethoven.
Oh, you're thinking the other way around. So the Play-Doh gets animated somehow.
Play-Doh gets animated, you plug it into the stereo and you see how it reacts.
That's a project.
That was yours, John.
Other questions?
Yeah. I'm curious whether you've looked at possibly, it's got the infrared sensors, but what about possibly radio frequencies so that you could connect the crickets to a computer somewhere, and you could, since they don't have as much processing, you could have them just send information about where they are and what they're doing, and the computer could, organize a squadron of crickets to, fly around or walk around.
Right. Yeah, we actually have played with radio. We have, with our bus system, we have a radio transmitter, radio receiver. So you can, if you had the full set of peripherals, you could easily start prototyping that stuff. The particular idea you mentioned of, like, robots reporting where they are, the where they are problem is actually hard because they don't know where they are. A lot of robotics research is robots that can look around them with various sensors and try to figure out where they are. By having a map or constructing a map. So that's just a hard problem. And you can solve that by having beacons and different systems for things to know. But
GPS in every room.
well, that would work for macro, where they are outside, but it doesn't work for where they are inside,
Well, you
really.
could do the same type, the same
Right.
idea with some sort of,
I'd say at the point where you've got all that stuff working, then you'll want something more powerful in the Cricket, because you've only got 2K of code space. But yeah, radios, doing different radio things is also, it's definitely fun. And
I mean, for example, to figure out where they are, you could have just to have them on a grid.
Yep.
With a light sensor that, the grid could be some sort of two-dimensional barcode that
you could do
read
that.
the light patterns on that, or some sort of braille thing or whatever.
Right.
In light dots.
Right. Yeah, you do the augmented environment. You can also put a camera in the ceiling looking down and have them carry, have them carry the barcodes.
Yeah. Like at the MIT museum, they've got a game that you can play, drop the ball into a hole and it reads where you are.
It's a little labyrinth game.
Oh, yeah.
It works with 2 knobs.
Yeah, okay.
So
Actually, I know one of the people who worked on that. Yeah, I've heard it described, but I've never seen it. I didn't realize it was set up. I should go there.
Yeah,
So it looks at your body, how you're moving your body, and then that controls the virtual...
It's where you're standing on the board. It's like a tilt board. You
Okay.
stand on it and it moves.
It's your center of gravity.
But
It's the camera that reads where you are and plugs that into the computer that makes it look like the thing that you're standing on tilts.
Right.
No weight sensors or anything.
Right.
Like that, just relative position.
Yes.
Is the military doing research on things like this?
I wouldn't really know. I mean, I'm sure they're doing stuff with, large numbers of cooperating autonomous robots. I'm sure they're doing that.